waiting for viewers, for the audience. Can you hear me? Yes. Three. At 10, we start. Four, five, five. We're still at 5. Come on, folks. 6. 5. Someone went away. Well, this will be the last, let's say, meaty lesson of probabilistic robotics. We will have the remaining part of the course. We will make a wrap up on all what we have seen so far. We will make examples of exams so that you come super prepared and score as high as possible. And we will present the projects. But this lesson is actually rather important because it captures most of the modern research that research and actually practical tools that are done in the domain of these probabilistic robotics things. The lesson will be dense because last time we jumped, and so let's start immediately. First topic of the lesson is graph slam and multi-pose registration. As you might imagine, this is a variant of the multi-point registration problem that we have addressed in the last lesson. So the multi-pose registration basically boils down to determining the configuration of a set of SE2 or SE3 poses that are mutually observing each other. Okay, so you could imagine one measurement between one pose and the next as if it was a relative transform that expresses the position of the target with respect to the position of the observer. Okay, and clearly these springs, these constraints are not at minimum energy in general, but we would like to find a configuration of poses that maximally satisfies this set of constraints in this case. Now it's quite important, the pose graph optimization, because it's at the base of modern SLAM systems. So typically a modern SLAM system describes a problem as a graph, where every node in the graph corresponds to a robot position and a measurement or a collection of measurements. Might be a laser measurements, an image, or an ensemble of things that the robot has seen at that position, right? And this is one component of our graph. And the graph is also consisting of edges. So like an edge between two nodes represents a special constraints between the two. Like you could imagine like a relative position between the two nodes that are potentially mutually observing the same thing. Okay? So like having boiled down in the end, being able to construct such a graph, which means being able to calculate the relative poses, or the relative poses between two nodes on the basis of the observations attached, and then being able to optimize the whole graph would resolve the graph-based slump problem. So in this figure, for instance, you see what happens if we record a data set based on laser into a medium scale buildings. I think these are 100 meters. Okay, this robot you could immediately see that has a very good odometry. See, these are what you observe here are just the laser scans overlaid based on the position estimated of the robot estimated by odometry. You could see that the robot in this figure has a very decent odometry because the corridors look straight and so on and so forth. But still, after walking for a long period of time, everything becomes inconsistent, and this is clearly due to the fact that odometry gives us only a prediction. Basically, the error accumulates over and over, and once you have made a mistake, you carry on this mistake forever. Okay. Now, how would a graph-based slump system work? Well, we will come to in a while to the way on how to construct the graph. For a moment, let's just imagine that an oracle gives us this graph that I repeat, imagine as a constellation of masses which represent the robot positions, and of springs that represent the equilibrium of positions between the two connected masses. So this is like an idea on how the graph looks like. You might see that there is a part, like this part, that follows the trajectory of the robot, right? Because clearly, if I deploy nodes, so now the nodes are not really visible because they are super dense, but these are nodes spawned along the trajectory of the robot. Okay. Clearly, once the robot moves on, it will add measurements, it will add constraints, so to say, between nearby poses, because these come from the odometry. So if I was in a certain location and I move to the next, for sure, if I have encoders on my wheels, I might tell something about the relative position of these two based on the encoder measurements. But also, we might have another component that is able, for instance, to determine the relative position of two scans, right? By means of scan matching. We have seen it. The many registration problems that we have addressed aimed at that. That might basically localize the robot in a local map or in a scan acquired in a previous time. Such a localization operation will give us the relative transform of one robot pose expressed in the other frame that correlates two poses, and this is, for instance, the case that you observe here and here. It's like what we could imagine is that we run a scan matcher with a scan matcher means a registration algorithm based on laser scans that takes this scan over here, and then aims at aligning them. By aligning the scans, you automatically determine a relative transformation between the robot positions that observes these scans. And these robot positions are the so-called loop closing constraints. The cool thing is that by proceeding in this way, you could abstract away which means not care of, the algorithms of the systems that you have used to compute such a relative constraints. And because it doesn't matter if all you want is a relative position of this robot and this robot in their respective local maps. You don't care whether this relative position is obtained by registering stereo images, for instance, or by registering scans, or by some other means. What you focus on is just the relative transformation that in this case will be pulled, right? Like so, this spring, given that we can visually see that this location here corresponds or is nearby this location over here. It's clear that the equilibrium point of the spring will be more or less in this location, but the spring at the current configuration is stretched because this is the actual initial guess that we have. Now, once we have constructed this graph that we could imagine as a graph of springs and masses, we could basically forget about the way that we use to construct such a graph. And we will see registration is one way of determining the edges, which means constructing the graph. And then what we could do simply is to run a least square optimization that determines, that moves the nodes of the graph so that they are maximally consistent with the constraints induced by the observation. And we would get something like that. You see, like this was all stretched. Now, if you let the springs relax, we reach this configuration. This configuration here resembles the trajectory, contains, in this case, the trajectory of the robot, not the last state, the entire trajectory of the robot. And what do you do with the trajectory? Well, having the trajectory constructing the map is quite straightforward, because in case of laser scans, well, you could just stick together the laser scans and obtain a map. If you would have images, but if the images would be perfectly registered, you could proceed having a high quality triangulation by triangulating the corresponding features, or you could do also something smarter, which is, there are systems which are called block correlation that try to get a dense reconstruction out of a pair of images or n images. Okay, so the idea is that I have raw data. Out of these raw data, eventually, while the system is processing, I construct this graph, and potentially I optimize this graph anytime that would give me a consistent, a coherent layout of the environment, which I can use basically to refine my further estimates. Now, this is one of the first images that, or first videos that I have shown during the, let me put myself upstairs and let me make myself a little bit smaller. This was one of the first videos that we have seen in the context of this course, and now I think it's quite clear that it's a graph-based slump system in action, where we have our robot which is constructing the blue graph. The dots that you see are the robot positions, the dot that you see from time to time, and any time when he re-enters in a known location, he tries to register the current scan with the previous scans acquired in that region, and if a successful match is found, it builds a loop closure, and which is a constraint, measurement between two nearby poses, and optimizes the corresponding graph. And this explains why sometimes the graph gets all moved. In this lecture, we will not address the aspect of graph construction. I will give you some ideas on how to do it, but just please think about all the registration systems that we have seen so far, and you could imagine that you have all the means to resolve the individual problems in graph construction. But we will focus on the back end, so on how to optimize such a graph that is coming, that contains basically the entire map. Okay. Clearly, during this process of mapping, it is mandatory, I would say, to have an optimized version of the map underneath, because having a properly aligned, a quite decent map might make our life much easier in determining the potential loop closures that we have seen that embody basically the data association problem in SLAM, and will render our map more beautiful, more nice by correlating the past and the future. So, and this block here is a general schema of how a graph-based SLAM system works. You get raw data that you could imagine that are, for instance, in these examples are odometry measurements and laser scans. And then you have a block that is in charge of constructing such a graph, or augmenting an existing graph that we normally call a map, that contains the processed information that comprise our that represent our environment, and that including also the trajectory of the robot. This block here can use to accomplish this task will produce basically the edges of the graph, because in this simplistic system the nodes are just like the nodes of the trajectory of the robot, so you know when to spawn a new node, because you might decide to spawn a new node each time the robot moved a little bit with respect to the last node you spawned. But what is tricky is adding the edges. Well, there are two classes of edges. The edges of the odometry are easy to be added because it's just the relative pose measurement between one robot position and the next. But the loop closing measurements, well, they might require, or constraints, they require a little bit more of tinkering, but you have the means, because we did a lot of registration algorithms so far. You could imagine that you could use ICP, you could use a combination of RANSAC and ICP in order to figure out whether two scans look alike and to put them one on top of the other, or two images look alike and to put them one on top of the other with a relative transfer. Now, just to expand on this, like it should be, what I would like to give you is like a quite precise understanding on how a graph within a graph-based LAMP system works. It's like we focus on what should be the work of a front end, which is the part in charge of constructing the graph, so this part over here. But clearly the front end takes as input and makes his life much easier if not only the raw data, but also the previous configuration of the map, which is coming from a backend, which is this module, which will be a Gauss-Newton algorithm or a variant, that will be in charge of iteratively and constantly updating this graph based on the new constraints and finding a minimum energy configuration. Like having a proper map will allow, or a reasonable estimate of the map will allow to lower the work that the front end has to do. Now, how is this graph constructed conceptually? Well, for sure it has n nodes, and each of these nodes is either a 2D or a 3D, or might be also a similarity, but for now just think about 2D or 3D transformation that represents the robot position at a certain time. Okay, so these are the nodes of my graph. Then there is a constraint that we will call, later we will call it factor, between two nodes of the graph. If these two nodes are connected by some sort of measurement. Such measurements might come if the robot, either from an odometry, which is a relative measurement that straightforwardly correlates one node to the next, or by means of a registration procedure that will rely on the information that we attach to a node that encode, for instance, the appearance of the environment in that particular position. Images, laser scans, whatever you want. So now let's imagine how we could establish such constraints. So let's consider the second case first, so the registration means. So we have these two nodes, one here, happily, xi, another node, xj, here. And these two nodes observed two pieces of word. Now, what we could do, remember that the constraints has to encode the relative position of this node with expressed in the frame of this node. Now, it becomes obvious that what you could do is to register the observations that I have made, and by registering the observations, you would move one node to the, like, You would determine basically implicitly a transformation of xj expressed in the reference frame of xi. And then, well, this edge, this relative transform, expresses the equilibrium position or a measurement that contains between xi and xj, which is calculated by processing the informations about the environment encoded in xi and in xj, namely by registering such informations. Okay? And it is clear that this little arrow, assuming that this is the reference frame of xi, will be a pose, right? Because xj has a rotation, a translation and a rotation as well. So it will be the relative pose of xj expressed in the reference frame of xi. This is one way we obtain the edges of the graph. And then another way of obtaining edges is straightforward, and I was mentioning before, is the odometry. Like the odometry, the relative motion that the robot goes from going from position I to position I plus 1. Well, that's an SE3 object that expresses naturally the position of this robot with respect to the position of this robot, or this robot position with respect to these other robot positions. The robot might be the same, or it has to be the same in this case. Okay? Now, once we have that, we might consider one thing. We have to boil down in the end the graph optimization problem in terms of a least square system. And we often, so far, disregarded this information matrix omega. But this information matrix omega is quite important because it encodes the certainty or the uncertainty that we have about the measurement along the different directions. Like, for instance, and this uncertainty could be used to recover some degrees of freedom that we might have by the registration problem. More specifically, just imagine that you have a scan matcher, so a laser scanner, that is walking into a featureless corridor, which is characterized just by two parallel walls. So now, if I give you another scan and you register them, you will figure out that basically sliding this scan along the corridor will provide the same, it will be equally consistent, so that you cannot really determine the translation of the robot along the corridor because the environment doesn't have enough structure. So like the corridor is featureless. Imagine that you're walking on a street which looks completely alike. You're not able to say at which distance along the street you are, at which point of the street you are. Okay, so if we programmed well our registration algorithm, while we try to register these two scans or these two observations, we will figure out that the response, the solution of my program will be characterized, yes, by a relative translation that registers the two scans, but not only, will also be characterized by the famous H inverse H, which is the covariance matrix of the solution. And the covariance matrix will reflect, in this particular case, if the system is well programmed and the right assumptions are made, will be something which is stretched along the axis of the corridor, just to encode that along that direction you don't know much. Okay? If in the post-graph optimization we embed this special information matrix, or we construct the information matrices of the constraints in a way that they do reflect the way the data are registered and the potential certainty that we have about the solution of the registration problem, then we will have a good behavior during the optimization, in a sense that even if all the nodes in a corridor are put one on top of each other, because maybe this is what the registration system will do, as long as you see something longer, like something that would stretch the corridor, maybe you walk in a forest that has a lot of other things on the bottom, So like you walk in a corridor and your robot basically thinks of staying in the same location. No? It stays in the same location, because the corridor all looks alike. But meanwhile, it's doing a lot of registration. So you put a lot of nodes. Each of these nodes is characterized by the measurement between these nodes are characterized by a covariance matrix which is long and thin. Then the robot moves out and starts walking in a forest, and then it walks in a forest which has a lot of structure, so it doesn't get lost along that direction. Then it goes back, and then it comes back to the corridor. Your loop closing system says, oh, I already know this corridor, fine. Now, so you have a corridor which is very concentrated over here, then a forest which is very long on the bottom, and then you go back and you see a corridor again. Now, an optimization algorithm, if with wrong covariance matrices, will create some sort of triangle of it, because it will say, oh, this position and this position are like that, and I just like find a minimum energy configuration just by stretching everything along this line. But if you encoded correctly the covariances along the top part, what you will have is that once you run this optimization, given that these constraints are much softer, the system will rectify basically your map, and the solution will look decently. If you have questions, just like write them in the chat. Some of my folks will answer. Okay, now this was to give you an idea that the information matrices are not really irrelevant. They completely control the behavior of the system. Just imagine that you put information matrices that are zero, and then basically any solution is good, like any other. Now, how are the edges in a pose graph? Well, the edges, or the measurements, are relative measurements between a pose xi and a pose xj, right? It's like as relative measurements, we could talk about the measurement zij, which basically expresses the position of the pose xj as if it was observed by xi. So zij is nothing else, going back to the slides, than this relative transform over here. And this will be the predicted measurement, okay? And attached to it, we will have an information matrix, omega ij. Trivially, you could get the zij directly by running ICP, or by running some of the registration algorithm that we have seen so far. Now, assuming that in my graph I have another node xj, and I know that xi and xj are connected by a measurement, this thing over here is the relative position at which the absolute position at which xi should see xj according to the measurement. Okay, so this is like a bar attached to xi that say, to me xj should be there. Okay. Then if I give you a position xj, you could immediately tell me the error of this measurement, because it's the difference between the prediction and the observation. Let me call this vector here eij. Okay, could also be the other way around. Okay, so now the goal of a pose graph is to find the assignment of poses to the nodes that minimizes the negative log likelihood of these observations that are now SE3 or SE2 observations that encode the relative position between two local maps. Okay. Now, this is our soup, right? This is what we can do, and that's therefore we will be doing that. Now, let's approach it with the least square methodology. Now we have a problem where the state is consisting of SE2, SE3 object. Why are you telling me so? Well, we just said that the goal of our system will be, or algorithm, will be to find the most likely configuration of a set of variables that are the robot positions. So given that each robot position is an SE2 or SE3 object, in this slide we will talk about SE3, well, that's the definition of state. Now, similar to the previous example that we have made about multi-point registration, the state will be a collection of these SE3 objects. Okay. or SE2 if you want. I decide to represent each of these objects in the canonical way, which is a rotation matrix and a translation vector. Because this representation, well, is basically the same in 2D and in 3D. And so, like, all achievements that we will reach with this in 3D could be straightforwardly ported in 2D if we want. Similarly, my perturbation vector, well, the perturbation vector should be big enough that I can move all elements in my state. Given that the inner degrees of freedom of a robot pose are 6, the translation, the 3D translation and the 3 angles, so 6, the perturbation vector, in order to move all the elements, will have to be equal to 6 times the number of poses in my state. And as always, I define the perturbation vector delta x to be consisting in many little blocks, x1, delta x1, delta x2, delta x3. Each of them will be having dimension 6. And similarly, and this is something we have already seen, we consider for each of these tiny translation vector a translation part and a rotation part. Having defined the state, having defined the perturbation, we might decide to define the perturbation in the usual way. So the perturbation on this ensemble of robot positions will be just, that is a manifold, will be just obtained by taking each of the prior robot position x and applying to the robot position the corresponding perturbation, right? Now in this this has to be flipped. I don't know why. There is another, but this time I can fix it because I can't stand it. So. Now you understand why it's a pain. Okay, I have to take this. Proportional font is evil. Let's see. Okay, better. We have our each robot position obtained by the previous robot position applying the perturbation, and we know how to do it already. Okay? Then, well, we have defined the state. Now it's our time to define the measurements. Well, the measurements, surprisingly, now we will encode, and the measurements are relative positions between two nodes in our graph, right? Relative positions are the same kind, let's say, of the poses in my graph, and so they are SE3 objects. So let me define a relative position, a measurement, as a measurement between the eth robot position and the jth robot position as belonging to SE3. And I decide, for coherence, to represent it as a rotation matrix and a translation vector. Oh, what a surprise! Okay, this will be the first implementation of our system. Okay, now this is the measurement. Remember, the measurement is where I expect that the robot position I sees the position j in its own reference frame. Okay, so if this is robot position I and this is robot position j, well, the relative position of j with respect to I will be this position here expressed in this reference frame. And this is a measurement because it comes from my registration algorithm or from my odometry. Okay, given this measurement, it's quite straightforward, I hope you see it, to determine to calculate the prediction. Remember, in order to calculate the prediction, I have to consider the state as fixed and say, assuming that the robot position xr is in this location, and the position, so xi is in this location, and the robot position xj is in this location, what is the measurement that I will observe? And it's quite straightforward to say that the measurement that I will observe will be the robot position xj expressed in the reference frame of the robot position xi. Okay, so having said that, the error function will be just the box minus between the prediction and sorry, I have to take this. Daniele, sto a lezione. Sì, sì. Having the error position, like the measurement, z is the measurement, the error is just the difference between the prediction, prediction and the observation. But given that we lie on a manifold space, in our case, the difference will have to be computed as a box minus. Now, remember how we define the box minus. To be coherent with the box plus, we could calculate the box minus just by taking two transformation matrices, like the one which is subtracted to the other, inverting zij, and multiplying it by the prediction. Basically, this function here will give us the this operation will give us the prediction expressed in the reference frame of the measurement. Okay, so if I take zij and I invert it, which is my prediction, and if I take which is my measurement, and I take my prediction and I multiply, let's say on the right or on the left, doesn't make much difference, then in case the zij is exactly the same of this object, which means that basically I have a zero error, then I will get the identity matrix. Because if this object here is equal to this object here, then taking the inverse of this and multiplying by that, well, gives me the identity. Because if this is, here I have a, and here I have a to the minus 1, if I do a times a to the minus 1, I get the identity. Okay? But this is only one way, one aspect to calculate the box minus. Well, basically this is a way to calculate the relative position of the prediction with respect to the measurement. But it's still a transformation matrix. In order to comply with the definition of the box minus, we will have to take this potentially small transformation matrix and mapping it back into Euler angles and into translations. Clearly, if I take the identity transformation and I map it back to Euler angles and translation, I get the zero vector. So the definition of the box minus is respected, or the box plus is respected. You might observe that this definition of the box minus is the dual of the box plus. So basically, what I'm doing is I am undoing the effects of the box plus. Okay? I'm happy because I defined my error function. So the error function is my prediction. I take my prediction, I take my measurement, and I box minus the two. And what I get is a 6D perturbation vector, because being the domain of the measurement a transformation matrix, we know that it has a minimum. It can be represented by 6 numbers. Okay. And this is a way on how to, in the last line, what you see is the error function at the perturbation, because remember that we have to put the box plus when we do this job, and the whole soup, basically, of our thing. So like the whole soup will be equal. So if you observe that object over here, this object over here, from here to here, this means take the position, take the previous robot position, which is this one, apply the perturbation to this robot position, so the box plus, and then take everything and invert it And in this way I have this part. This block over here means do exactly the same on the other robot position. So take the robot position, apply the perturbation, and leave it as it is. And then you have to apply to this object. So then I'm done with that. Then you have to box minus these two objects, and then we have just defined that the box minus between two transforms is take one transform, invert it, multiply it by the other, and then calculate its minimal representation. So this will be the box minus. So this equation here represents the box minus between this object and this object here at the perturbation, which is on the right. Okay. Now, by using the properties of the inversion, we know that the inverse of this is equal to you could remove the parentheses if you take this object here and you invert it and you put it first. Take this object here, you invert it, and you put it after. Okay. And what we have is the complete error function for a measurement in this pose graph. Okay. Are we done? Almost. Almost in a sense that we now need to calculate the Jacobians. Now, if you remember how complicated it is to calculate the Jacobians of, just think about all these objects over here. If you remember how complicated it is to the equation or the formulas that take a rotation matrix and extract Euler angles, and if you imagine that you have to calculate the derivative of this function, then you start crying. Okay? Indeed, it can be done, but it's a little bit a long process. And I don't want to spend too much time in calculating derivatives, but it should be like, you should have the sensibility that the more complicated the function, the more complicated the Jacobian will be. However, we could immediately say something about the structure of the Jacobian of one measurement. Remember that one measurement, one of these measurements over here, depends between the pose I and the pose J, depends only on two robot positions, the position I and the position J. Okay, guys? Similarly to what we have seen in the post-pose registration, this will have an impact on the Jacobian that will be 6, because I'm measuring a vector, because my error vector is tall 6, because 6 is the minimal perturbation for an object in SE3. And I obtain it by applying the dual of V to T, which is T to V transform to vector. The inverse, actually. And so this is the height, and the structure, well, the structure will be consisting of 6 by 6 blocks, because each of the blocks of this Jacobian prominates or depends on one of the initial blocks of the delta xi, j, whatever that are in the system. Okay, each robot position, and there will be two non-zero blocks. Not all these blocks are 6 by 6. One non-zero block will be the block corresponding to the pose xi, and another non-zero block will be corresponding to the pose xj. Okay? The rest will be beautifully zero. Now, clearly, let me call this derivative here ji, and this derivative here j, ij. Okay? Now, if you remember something about the information matrix shift, also in this case our domain is a manifold, right? Our measurement domain is a manifold. So being it a manifold, this means that we cannot straightforwardly use the information matrix which will be attached to my measurement, but at every point in time I will have to apply this, this rotation, as we have seen in the exercise, in the lesson on least squares at the manifold. So like what happens is that while I want to construct my quadratic form, I will have to consider my prediction, which I call Z dot ij, to calculate the Jacobian that can project a matrix expressed in the system of the transformations, which will be a 12 by matrix as I have in theory 12 numbers, because you have 12 numbers in Z, 12 active numbers R and T, and so I will have a covariance matrix which will be 12 by 12, and I have to project it back to an object which is to an error which has dimension 6. So like to do so, well, I take my predicted measurement, I take my actual measurement Z, and I derive with respect to the actual measurement. I get the Jacobian, and I do first order error propagation by taking the information matrix and passing it back, passing it through this linear function, and inverting it again. Okay? And this will give me the famous omega tilde. Long, complicated. When I have to construct the H matrix and the B vector for one measurement, similar to what we have done for the multi-point registration, I will have in this case 4 blocks. 4 blocks, one block that corresponds to the JJ variable, one block that corresponds to the pair IJ, one block that corresponds to the JJ, and these are symmetric. And similar I will have for B. Okay, so even in this case, the sparsity of the structure is preserved. If you don't remember this structure of the Jacobian, I recommend you to have a look to the lesson on multi-pose registration, where we talked a little bit about that. Now, it's a long thing. Calculating these Jacobians and giving you the solutions gives me nausea. So instead of doing that, I offer you a way to have a running solution without doing all this work. And this solution is called the Chordal distance. Now, what is the bad part of this derivative over here? The bad part is this T2V here, because so far we were straightforwardly able to calculate Jacobians which were involving this object over here, also Jacobians that were involving these objects over here. But the thing that Z is a linear transformation, because this you calculate only once, is a constant for you, and so it will be multiplying the Jacobians by a constant matrix, but this is the bad thing. So now the question is now, how could we get rid of the bad thing? We could get rid of this bad thing just by bloating up our error vector. And if we say, you know what, if I take 2 rotation matrices, right, and I consider the 12 active component of 2 transformation matrices, so I have 12 numbers inside, because the last row I can't ignore. Well, how many elements do I have in this object? I have 12 elements, no? 3 by 4. Okay. And what happens if 2 transformation matrices are the same and I subtract each other, or I subtract these 12 components? Well, I get 0. So I'm consistent with the error metric, that if 2 things are the same, well, then their difference should be 0. What does it mean to subtract 2 transformation matrices? Well, the transformation matrix is composed by 2 aspects. One aspect is the rotation matrix, and the other aspect is the translation vector. Now, if I subtract the 2 translation vectors, the meaning is quite obvious. It's the difference in position between the 2. If I subtract the 2 rotation matrices, the difference is a little bit more subtle, but it's still very easy to visualize. Now, if you look at a rotation matrix, well, you could see it as 3 vectors like that in the space. Now, 3 vectors, unit vectors, which are orthogonal. If I have another rotation matrix, let's say this other one, and I subtract the corresponding vectors, well, the difference between the first column and the second column of the matrix will be this delta element over here, between these 2. Then the second one will be the delta element between the 2 corresponding items, and the third will be the same. So I have a chordal distance, right? That we have already encountered. We have encountered it when I was talking about the direction vectors. And likely calculating this new metric, so we bloated up the error vector to be dimension 12, and we said that the error vector will be just 12 components, right? And it will be calculated just by taking the measurement, which is Z, which is a 3D transformation matrix, and the prediction, which is another 3D transformation matrix, and we subtract the corresponding components, the 12 corresponding components. But yeah, but it's not a vector. Well, we will have to make it flat. Okay, so let's say that I have a generic transformation X, which is represented in this way. I have a rotation matrix, a translation vector, and the famous one here. I could see my rotation matrix as Y. No, it's not cooperative. My rotation matrix are as 3-column vector R1, R2, and R3. I could introduce an operator, which is super straightforward, super stupid, which I call flatten of X, that given a transformation matrix returns me this vector over here, R1, R2, R3, and T. How big is this boy? Well, 12, because each of these things is has dimension 3 and this has dimension 3. Okay? Very good. Okay, this is the first thing that we do. Now, let me introduce a function, g, don't know why, g, that expresses the prediction between a robot position I and the robot position j, so the measurement about the position of j that I should do if I were in I, which is the product of these two objects over here. Basically, this is our prediction. Let me define the prediction vector hij as a flattening of this result over here. So I take the prediction, which is a transformation matrix, and I turn it into a 12D vector. A 12D vector is not a manifold, it's not a complicated thing, it's just a brutal 12D vector. Okay? What I can do in this case is just calculate, it's a Euclidean vector, right? Well, if it's Euclidean, I can get rid of the box minus, and so I can get rid also the T2V. So I could define my error function as flatten of the prediction minus flatten of the measurement. What I will be doing is subtracting two transformation matrices which have been turned into 12D vectors. This will clearly increase the size, the dimension of our error vector to 12, right? Because if this is large 12, this also has to be, this is tall 12, this is also has to be tall 12. And similarly also the Jacobian will be tall 12. The blocks, however, will be large 6, because the number of active variables, remember, are the active variables in the perturbation, which we preserve. So my new Jacobian will be consisting of blocks which are 12 by 6. And equivalently to what I have done for the non-Chordal case, I observe that given that this error function depends only on the pose xi and xj, this structure here will be mostly 0 and non-zero only in the position I and the position j. Clear? Yeah, I ask questions to myself because I know you will not answer. Okay, this looks much more digestible than this thing over here. Now we are, let's say, almost ready to calculate the Jacobian. To calculate the Jacobian, we start expanding. Remember that the Jacobian is the derivative of the error function at the perturbation with respect to the perturbation. We will be, as usual, calculating a Jacobian of only one error term, with respect to the generic variables I and the generic variable j. This error term will be consisting in... Let's first work on the inner function, which we call g, that returns our transformation matrix of the prediction, and let's write down g at the perturbations. Okay. Now, if you apply our usual definition of the box plus, we know that the box plus in a pose, you do it by calculating the transformation metric corresponding to the perturbation and multiplying, in this case, to the left by the corresponding variable, right? So if we do the box plus expansion, we could write down this formula over here, where in this case, considering that one of the two components was the inverse of the other, we applied the inverse to the left element, and this made the v2t moving to the middle. Now you can also observe, and if you calculate the sum derivative, the v2t if you calculate the v2t of delta x, the v2t of the inverse of the v2t of delta x, you will figure out that this formula here is very similar to, or it has the same value of v2t of minus delta x for small x, for small delta x. So this object here and this object here, so v2t to the delta x to the v2t of delta x to the minus 1 is more or less equal to v2t of minus delta x. Okay? But just to have an intuition about it, remember what was happening to the Jacobian. The Jacobian was coming out to be a skew symmetric matrix around the vector, right? Like so now, if the vector, the axis flips, also the skew symmetric matrix will flip. It's just to have an idea on why v2t is the same. v2t of the opposite for small perturbation is the same as v2t of the inverse for small perturbation is equal to the v2t of the opposite. And now we can do the products. That's what we will be doing. We do the products. So this object over here is the expansion of xi to the minus 1, where we have r transpose minus r transpose ti. No? This object here is the expansion of t2v to the minus 1, which we said to be equal to t2v to v2v to v2t to the minus 1, which we this is v2t. So this object here is this actually, which we said to be equal to the same of the opposite, so we could write it in this form. This object here expands to that according to the notation we have introduced so far, and the last object here expands to this object over here. We're just expanding and seeing what the different things mean. Okay, I have to fix this, but I will not fix it now. Now, what happens when we derive this equation here with respect to delta alpha and delta t, evaluating them in 0? Remember that once we derive, this matrix here disappears because we are deriving with respect to alpha I and with respect to ti. Okay? So this object here is evaluated in 0, so it becomes the identity. Well, if we notice that, we will find a number. Okay? We will find a number. and we will have to evaluate this number with respect to alpha and t, which are equal to 0. Okay. Presumably, you know that the derivative of minus something is equal to minus the derivative of something, right? And this is like what we expect to have. So once we derive this object with respect to this component over here, and in particular to this and to this, we will find a certain matrix or a stack of matrices in general. If we do the derivation with respect to this other object over here, we'll find another set of matrices. But if you observe that this matrix here, looked in the alpha I and Ti, is equal to this matrix over here, looking in alpha j and Tj, only with the opposite in front, we might straightforwardly say that the derivative of this function with respect to alpha I and Ti evaluated in 0 is equal to minus the derivative of this function calculated with respect to alpha j and Tj evaluated in 0. So basically the derivative of this function here with respect to xi is equal to the opposite of the derivative of this function here evaluated with respect to xj. And this is a consequence of this statement over here. So it's a good thing, because this means that we don't have to calculate anymore two derivative objects, but we can just like focus on calculating one single block, being the other block the opposite. Now there is a mistake in this slide. This is not t to v, it's v to t, also here. Alright, now let's calculate the derivative of this matrix here with respect to the second term, alpha j and tj. Okay, so why doing so? Because this has a minus in front, and a minus disturbs me. Given that one is the opposite of the other, I can just start from the easier one, or the less boring one. And unfortunately, we have to do the products. We have to do the products of all the things which were in here. And in particular, by doing the products, we will find the block which represents the global rotation of this thing, which is we will call R, and a block that represents the global translation of this product, which we will call T. Okay? By doing these products, if you take a pen and paper and you do these products, you will figure out that the derivative of G with respect to delta xj has the following form. So like this means this is the first matrix, this is the second matrix, the matrix of the perturbation, this is the third matrix. Now if you do the products, well, the products of the rotation is this times this times this. Quite fine. Now the product of the translation is long, is Ri transposed that multiplies the product of these two. Like, so you take Tj, you multiply by R of alpha j, and then you sum delta Tj, and then you have resolved the translation vector for this part. Then you take everything and then you apply the last part. So like you have to take this vector multiplied by R and then subtracting this part over here. Then in the end you get this transformation matrix over here, which is a long thing. Like, not long, takes a little bit, just simple, straightforward calculations, I think. Okay, so we have found an equation, right? An equation that is coherent with what we expect, because we have a rotation matrix block, and this object over here, it's clearly a translation vector. Okay? Very good. We're not done. We need to derive it, right? Now we are now preparing for the derivation. Now, preparing for the derivation, what will be the derivative of this object over here? How would you visualize? Given that G is a transformation matrix, consisting of R, and consisting of t, the derivative of this object here with respect to one component of the derivation, with respect, for instance, with respect to alpha j x, will be by itself a transformation matrix. Okay? So I could visualize it as a stack of 3 by 4 matrices. How many? One for each component I'm deriving with respect to. So like I have 3 here and 3 here. So the derivative of this object will be consisting of 6 3 by 4 matrices. One with respect to alpha x, one with respect to alpha y, one with respect to alpha z, and then 3 with respect to the components in the translation. Okay? This will be my object. So let's start to calculate these derivatives one by one, these 12 derivatives. But still, you might guess that we will help us with the formulas, right, of the rotation matrices, and in particular, consider that we want to calculate this derivative in a with respect to a perturbation evaluated in 0. So I here copied the rotation matrices with respect to x, to y, to z. Here I've copied the derivatives, and here I have copied the corresponding derivatives evaluated in 0, which is basically this thing evaluated in theta equals to 0. Now, if we want to calculate the derivative of this function, this thing over here, with respect to tx, or to alpha x, for instance, well, we will have to take this whole object over here and replace this matrix here with the derivative of the rotation matrix with respect to alpha x, with alpha x evaluated in 0. And we will have to do the same in this other part. Okay? Similarly, if we want to compute the derivative with respect to alpha y, we will have to replace in this equation here to this r of alpha j, r prime of alpha y evaluated in 0, and also here. So by doing this game, we manage rather quickly to construct the 6 matrices representing my derivative. One of these matrices, each matrix will encode the derivative of my g function with respect to one of the elements. Okay? Now, what about t? Well, what about t? You can see it here. The delta t. Delta t, if I derive this object with respect to delta t, this component here will be 0. This component here, so if I do the product, I have r transpose r alpha tj, which if I derive it with respect to delta t becomes a 0. So the only active components in the derivative of this object with respect to delta t is ri and delta tj. Okay? And therefore, if I compute the derivative, and in particular, if I derive delta t with respect to delta t, I have the identity. Or if I derive with respect to delta tx, I have the vector 1, 0, 0, which is the first column of the identity, 0, 1, 0, which is the second column, and 0, 0, 1, which is the third column. And this basically expands the 6 Jacobians of our formulation, of our G. What do you do with these 6 Jacobian? Well, consider that in order to calculate the Jacobian of the prediction, the relation between the G function and the H function is just this flattening operator that takes a matrix and slices it in 12, so puts it into a 12 vector, right? So it's quite straightforward to, and you don't need to do calculations, you just need to move elements. So it's quite straightforward to say, okay, well, the the H is related to G only through a flattening, as is explained here. Equivalently, their derivatives will be related only by a flattening. In this way, we can arrange these 3 by 12 matrices, 3 by 4 matrices into a 12 by 6 vector, where the first component will be obtained by taking the derivative of G with respect to the x component of the translation and flattening it. We do the same for y, we do the same for z, alpha x, alpha y, alpha z. And this is consistently a 12, because it's told 12, because each of these objects here has 12 components, 12 by 6 items. Okay, guys? Very good. We know that also the Jacobian with respect to I is the opposite, so we don't need to compute it. We just take the other one and we put a minus in front, or even don't do it, because then we can just put the minus in the calculations we might need to do. Okay? Very good. So, well, and this is, if you put everything together, all the slides of before, you will find out that the Jacobian, the final Jacobian with respect to xj, has this particular form. You have r prime x, r prime y, r prime z, which are these 3 components, which get stacked in this part of the transformation matrix. Here you have minus ri transposed, and here you have minus Ri transpose, which is multiplied by the skew symmetric matrix. Here it comes of Tj. Okay? I mean, how do you come from here to here? Well, just use these formulas and use this definition. Do the calculations, and you will find out that this is my final Jacobian, which is consistently a 12 by 6 matrix. Okay? Okay. This was written conclusions. Okay, now this is the conclusion of this part, but it's not the conclusion, because this lesson is supposed to continue with the second topic, which is the factor graphs, and for which I prepared, which is the closing and probably most important topic of the course. And I will be closing with an exercise. If I don't manage to do the exercise, we will do the exercise on Tuesday. Okay? What do you have to keep in mind is that we managed to boil down everything into the least square notation, and also I think it was a useful wrap-up of the thing. The pose constraint, or the pose measurement, is nothing else than a measurement, than a sensor that from a robot position senses the position of another robot. You could imagine it in this way. And in this part of the lesson, we have been modeling the pose graph problem, and in particular, we provided a solution, a complete solution for the chordal relaxation of the problem. And now, the second part. Please don't lose stamina, less. Don't lose stamina, because we will have to now go on factor graphs, which are here. Yes, they are here. Which I call sparse optimization. I will rename it sparse optimization factor graphs. Change title of the slide. Also because it's consistent with the finding. Okay, now you have seen that graphs or matrices that have a special structure start to appear in our class of problems. You have to consider that classical bundle adjustment problem, where you want to determine it's like a multi-point, only that you observe only the point projections, might involve hundreds or thousands of cameras and millions of landmarks. And this is clearly not easy to solve on the one hand. We have seen problems that include post graphs. Imagine that a post graph might have easily thousands and thousands of nodes. We have seen a post landmark examples, but plenty of them. And in general, when these systems start to be very large, so when I have a high number of variables, well, in the end, all these systems boil down to the solution of a linear system. And you know that the solution of a linear system is a thing that it might be expensive and depends on the size, on the dimension of the linear system. Now, if I have thousands of poses into a 3D, into an SE3 problem, I have 6,000 variables, basically, one for each component of a pose. And then this will be, 6,000 by 6,000 matrix, which starts to be painful, no? Now imagine that I have 20,000, and then you end up that you can't even store this object, or maybe it's quite challenging just to handle. And then doing an inversion or doing a linear system solution starts to be hell. Okay. Luckily, we have seen, especially in the pose landmark multi-pose registration problem, that the H matrix has a number of, in a certain class of problems, has a number of non-zero blocks, which is much smaller than the total number of blocks in the matrix, which grows quadratically. Like, the rationale behind that is that if each time you observe a landmark, you add assuming that all landmarks are already in the state, right? Or all poses everything is already in the state. So you have a system that contains all robot positions so far and all landmark positions so far. The state doesn't mean that the estimate is correct. Now, once you observe a landmark, what happens is that you calculate a component of the H matrix that depends on the observing robot position and on the observed landmark position. Okay, and the position of this block here, or this Jacobian here, will contribute to the total H matrix by the J omega J component that we have seen in the last lesson will only influence the diagonal part and also the off-diagonal part that is at the intersection of the observing robot pose and the observed landmark. Okay? So, if I add the measurement, I'm only adding one more block to the matrix in general. Or in general, I'm adding a linear number of blocks. So now, observe that in a large class of problems, and in particular in the SLAM-like problems, the sensor field of the robot is limited. So not that if the robot is in a room, it can't see the building on the other side of the street. It will only observe things that are in the room, right? And it will observe a number of new things based on how much it moves, right? So like if I stand still, well, I observe always the same stuff. I could imagine that each time I move, in general, I observe something that a constant number of items, because the field of view is limited, and so I can't observe more than 100 things in one opening of my eyes. So I observe a number of landmarks or re-observe, which is at most constant, or which is upper bounded in a sense. But is upper bounded, which means that the number of factors that I insert, or the number of observations that corresponds to a new pose, is at most n, which means that after n poses, n, no? Come Nicola, n poses, I will have introduced at most n times n new factors, which then translate in a number of variables, which is proportional, the number of non-zero blocks in the H matrix of the diagonal, which is proportional to the number of poses of the robot. Okay, so if at each pose I observe 10 landmarks, well, at most I will throw in 10 measurements, and if each measurement adds a constant number, adds one non-zero block to the H matrix, well, then I'm done. Okay, now, if I add 1,000 poses, my the non-zero block, the dimension of my matrix will be in 3D 6,000. Okay. If I add for each pose I see, if let's say, if for each pose I observe at most 10 landmarks, which also then the number of non-zero blocks added by this by this observation will be dimension of a landmark times the dimension, so will be equal to the number of to 10 times the number of the poses, which is 6,000. So on the one hand I have a matrix which is 6,000 by 6,000, and on the other hand I know that I will have within this matrix only 6,000, or what I said, I will have only 10 times 1,000, so 10,000 non-zero blocks. So 6,000 by 6,000 is a growth which is quadratic. The number of non-zero elements that I throw in grows linearly with the number of poses, which means that the more I explore, the more the system will be sparse. So the more non-zero blocks will I have, or the more occupied blocks I will have inside inside my system. So like most of this H matrix is zero, and there must be something to do if an H matrix is zero, or is if a matrix has a lot of non-zero elements. Just like think about yourself when you were solving the linear algebra problems and someone was asking you to solve a linear system, and if the system matrix had a lot of zero, you were immediately smiling because you were saying, oh, this I'm gonna do it in less time. The computer could do the same. Now, it turns out that in many cases, so this post-post problem, this bundle adjustment problem, and in general, are characterize the structure of a large set of problems in robotics. And these problems are problems where you have locality, so where basically you have measurements that depend, you have a huge state vector, but the individual measurements depend only on a relatively small set of variables in your state. In particular, we have seen in case of multi-point registration, we have seen that one measurement were depending on one robot position and one landmark position. In the case of the post-graph problems, we have seen that one measurement depends on a robot position and another robot position. But in my state vector, I might have 100 robot positions. Okay? And so if my measurement function only depends on a subset of the state variables, then I might consider to generalize this and to have a generic methodology that you find also in the paper that we sub-ministered you for as a backup for the second part of the course, which is the so-called factor graphs. Now, let's generalize a second, and let's for a moment just hide a little bit the prediction function and think only about the error function. Because in the end, what we are interested in is the error function, in a sense that the prediction function is only h, is only a means to reach the e. Okay? In the end, what we are minimizing is the e. Okay? Which in the simple case is obtained by h minus z. But if not, I can just close my eyes and think e. Okay. Now, in general, let's say that I have a set of state variables that I call xt. This is all my state variables, which will be consisting of a variable xt1, xt2, xt3, and they can be arbitrary. One can be a point, one can be a landmark, another one could be calibration parameters, whatever you want. You have this constellation of variables that are involved in your system to estimate, that you want to estimate. Then you have a set of measurements that come potentially also from different sensors. You might also consider to mix the odometry and the landmarks, right? Makes perfectly sense. You could have, you could introduce, you were doing it in the Kalman filter when you had a robot with the odometry and you were able to observe landmarks. Why the hell shouldn't I be able to use my odometry observation into a least square machinery? There's no reason. In the end, I could just have a certain number of error functions. The generic error function, E, I call it EK to denote that this is the kth error function, will depend on a subset of variables of the state, which I will call, not all of them, these are all, which will only depend on xk1, xk2, blah, 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 xkq, just the last one of the list. And of course, this set of variables will be included, will be a subset of the total number of variables. Like, imagine that I have a system where I have an odometry sensor and a landmark sensor. Okay, and I want to formulate this registration problem, this multi-posting, whatever, that incorporates both measurements. Then I will have two classes of error function. One error function that arises from my landmark measurement sensor, and it will basically be described, assuming that you have a landmark in a certain position and you have a robot in a certain position, well, where the robot will be observing the landmark? Here. And then what is the difference between the prediction and the observation? That will be the error function. This error function will clearly depend only on XR, position of the robot, and XL, the position of the landmark. Only two among the set. Okay? And this is one. It will have dimension 3. No? Landmark 3 dimension. Good. Then I also buy, or I already have it, and it's for cheap, I have an odometry on my robot. For simplicity, let's say that the odometry shoots me a full 6D odometry in our universe. Could be an IMU or something. And therefore, an odometry measurement, if I reason in the context of least squares, I can't reason anymore in terms of the control transition. I have to revert it. I have to say, okay, assuming that I have the position at time t, the position of time t plus 1, and then what would be the odometry measurement that I would predict, knowing that at xt I'm here and xt plus 1 I'm here. This will allow us to generate our prediction. And then having the h. Having the h, we could calculate the error, right? As we have done in the post business. And still, this is another class of measurement that I can throw into my system. In general, heterogeneous. The only aspect that they share is that they have a subset of variables. In case of the odometry, clearly the variables involved, this xk of the odometry, will be consisting of two variables that are one pose and the next. Okay? Now, what we want to do, straightforward, and each of these measurements is attached to his own information matrix. And what we want to do is to find the minimum of the log likelihood of this distribution, which is a least square problem, as you might observe, and this is just a generalization of the mechanism of the things that we have seen for the Gauss-Newton-like family of algorithms, right? And in fact, factor graphs, they don't absolutely introduce a new method, they just introduce a common way to formalize the problem. Okay? The method stays the one that you were to describe the problem. The method stays the one that you have learned, or maybe others, but it's a way to describe the problem. Now, let's imagine how we can, and this formulation includes, if you think about it, all problems that we have addressed so far. It includes the pose-pose, the multi-pose, but it also includes the ICP version of the things. With the ICP, only that this set X was consisting of only one variable that was appearing all over the game. Now, how could we represent this function, just to see it? We could represent it with a graph. So this equation here, or this equation here, can be visualized by a graph. And graphs are nice because they provide a visual feedback. This is the factor graph corresponding to a pose landmark slump problem, where the robot is moving in an environment, and it is equipped with a odometry sensor. Pose landmark, sorry. I don't have yet an odometry, yes. This factor graph here describes the pose landmark. I have just a robot without odometry, so it's a multi-point registration. Now, the variables in the factor graph are anything I want to estimate. So I will have a robot position 1, robot position 2, 3. This is the chain of my robot positions. And equally, I will have a chain of landmarks, the landmark 1, landmark 2, landmark 3. And what I can say is that if from the first robot position I observe the first landmark, then there will be a measurement in between. And this measurement, this factor, depends on the landmark measured by robot 1, the landmark 1 measured by robot 1, denoted by ZL11. Similarly, if I have a robot position, I observe the same landmark from the second robot position, I will have another edge, let's say this way. But let's not call it edge, let's call this, let's promote this thing here, this connection here, by putting a node in between, right? And in this node we will store the information. So these square nodes, which encode the measurements, and in fact they encode the error function, because to each measurement there is attached the corresponding error function, these we will be calling factors. Okay? Very good. Observe that a measurement might also depend from 3 variables. Let's say that my robot observes a landmark through an unknown set of camera parameters. If this would be the case, I would have to put another variable here to represent the set of parameters of the camera that I want to estimate. And then, assuming that I know the robot position, I know the landmark position, and I know the camera parameters, then I could predict the landmark position, the measurement, the projection, that then in the end has to be subtracted to the measurement to give me the error. So in this case I would have this block here that contains, that connects 3 variables, also the camera parameters that are here. But this is an example on how to represent pose landmarks. How to represent, if we add an odometry to our system? Well, not much happens. If we add an odometry, we have the same set of variables, the robot positions and the landmark positions. But we also have measurements. We have measurements that correlate a robot position to the next. And these measurements will be represented once again as factors. And this, we will call it a factor ZR, that connects the robot position XR1 with the robot position XR2, and it will be consistent to represent or to measure the error between an odometry measurement of the robot moving from here to here. And let's say it's a SE3 object, a pose thing that we have already seen. Okay? Programmatically, what we have to do is only to add to the generic H matrix the blocks of this thing, but we will see it in a while. Okay? Very good. Now, as I mentioned, this representation is so the factor graph is this representation here is called factor graph. It can be used to represent arbitrary factored functions, and it's a bipartite graph in a sense that the nodes have two colors, like this pink, this yellowish here is used for the variables, and this bluish here is used for the measurements. And it's bipartite in a sense that you cannot reach a measurement, orange measurement from another orange measurement if you don't pass first, so an orange node with another orange node, if you don't first pass through a blue node. This means bipartite. Okay. Clearly, if I would cast the very same problem and I would have odometry, unknown odometry parameters, well, like so, this is a landmark plus odometry, I could have here another variable, which is the odometry parameters, and then these odometry parameters will influence the odometry measurement that I do between when I move from XR1 to XR2, and so like it will be a third edge of this block over here. Okay. In general, one of these factors will contribute to the H matrix. Consider the formulation of a factor and consider that a factor which represents one of these E here, and remember that the E only depends on a subset of the state variables. One of these factors here will in general influence a number of blocks of the H matrix, which is equal or proportional to the square of the variables involved. Because if you take this, let's say this is a Jacobian of a generic factor. This factor here depends on the variable k1, k2, kq, right? Which are potentially scattered in my ordering of the variable set. Now, if I multiply this by itself, transposed, then I will figure out that it's 0 mostly everywhere, despite when in the correspondence of the cross when I have in the blocks where both indices appear to the index set here. Okay, so k1 k1, k1 ki, kq kq. In case of two measurements, well, then this thing will give me only 4 blocks. Of course, I never calculate the lower part of the matrix because I know that the matrix is symmetric. Okay? And similarly, I will have for the B vector. Like now, this class of things induces or allows to highlight the sparsity pattern of H. And we can imagine that the H matrix will receive a contribution, a number of non-zero elements, which is proportional to the number of factors, okay? Which are the E functions. Now, what happens when you calculate the global H matrix? Now, this figure here, the red denotes an occupied block in the Jacobian, and the blue denotes an empty block. What happens when you solve your linear system, you assemble your system matrix? Well, you're going to assemble the B vector and the H. The H is, in general, sparse, and it will stay sparse, because basically the number of non-zero blocks grows with the number of variables, and the number of factors grows with the number of variables. What happens is that each time you add a component to the B vector, in the end, you are making the corresponding blocks dirty. And given that in general all variables are appearing in the B vector will be in general dense. In contrast, the H matrix will receive a number of contribution, which is basically at most a number of blocks which is equal to Q square, right? But actually most of them are on the diagonal, and and then I will have to, where Q is the dimension of a factor. And in general, you will have a dense diagonal, but you will have a very sparse structure in the upper part. Now, as I was mentioning before, the number of, in SLAM, or in this class of problems, the number of non-zero blocks in H depends on the number of measurements, and this, given that each measurement leads to a factor, and each factor makes it dirty at a constant number of elements in H, well, I will have the number of non-zero blocks the number of non-zero blocks will grow linearly with the trajectory of my robot, while the potential number of non-zero blocks of H of my matrix will grow quadratically, because it's a matrix, it's not a vector. Okay? And then basically realizing that the H matrix is sparse allow us to use smart ways to solve this linear system. Now, it's out of the scope of this course to introduce sparse linear solvers, but if you are interested, I will give you a very introductory nice paper on the topic. What typically, what you can imagine is that once you solve a linear system, in the end you never solve it directly. You always pass through some sort of factorization. What classical systems, what MATLAB does, when realizes that the matrix of a system is symmetric, the first thing it tries is to use the Cholesky decomposition. So, because the Cholesky decomposition gives you a stable, numerically stable solution if H is positive definite. So it takes H, it computes the Cholesky decomposition of H, L transpose. Recall that L is a lower triangular matrix, and this is an upper triangular matrix being the transpose of the other. Then after I perform this decomposition, I can go back to my linear system and substitute H with L transpose, which I find it here. And then I solve the system in two steps. At the very first step, I ignore this part, and I call it Y. And then I solve a triangular system that is lower triangular, and I solve this is a vector, right? I solve for Y, no? And I determine this fantastic solution. Once I have found Y, which is the solution of the lower triangular, this is called back substitution, I do a forward substitution, which means I take Y and I solve the linear system L transpose delta X equals to Y, which derives from this definition over here. And then I have found my my solution. Okay, now you can imagine that this operation of solving the linear system, assuming that L is sparse, no? That I have a few number of elements in L. Then I can imagine that an algorithm that solves a matrix, a triangular matrix from a system consisting of the product between a lower triangular matrix and a vector equals a coefficient, right? Like, then it would be straightforward. What would you do is that you solve the first equation, that it's immediate, is on the top. Then you take the result of this equation, you put it in the coefficient vector, and you shift the coefficient vector on the other side, which will be this part of L, and then you solve, and then you repeat. So each time you make the system smaller and smaller, right? This will be the way to solve it. And then you can imagine that this operation here is dominated by the number, because you don't do stupid things, you keep sparse structures also in memory, is dominated by the number of non-zero. This operation of solving one of these equations is dominated by the number of non-zero elements in L, right? Because the the more numbers, non-zero numbers that I have in L, the more operations I have to perform. Providing you with the Cholesky factorization of H doesn't solve the problems at all. Because if you have, if H is sparse, once you calculate the Cholesky decomposition of H, L will not be in general sparse. L might be dense. And so this means two things. First, that it takes ages to compute L, because it's dense. And so you have very few elements in H, but then once you want to solve the system, everything blows up. That's not nice. And then the second thing is that, assuming that you have a super fast way to calculate this, which is impossible, then you have to solve the linear system with back propagation and forward propagation. So solve triangular and lower triangular and higher upper triangular. And then still, also in this case, you lose time, because you lose a time which is proportional to the number of non-zero elements in L. So what can we do? Well, that's a thing that what can we do? That's a game that comes up from the observation of these things, which is basically the sparsity, which is the non-zero element, the number of non-zero elements of L, depends on the number of non-zero elements in H, but it's strongly influenced by the order. Now, to understand this, now I will try to do. Let's see if I managed once I managed to write something. Let's see if I can. If this is visible. Is it visible? Yes. And now I change perspective. Yes. Okay. Oh, perfect. Now, let's imagine that we have a linear system which has this pattern. Okay. Can you see anything? Yes, I think you can see. So, like, this is the number. This is my A matrix. This is my X vector, and this is my B vector. Okay. Now, if I want to solve this system with a traditional way, what I would have to do is, like, okay, I start from the first line. I eliminate the first component. Let's say that we do Gauss-Newton elimination. So, like, my game would be to set this component to 0, right? And then to delete everything below. Okay. So I set this component. So I set this component to 1. So I take the I multiply this line of the matrix by the inverse of the first component, so that it becomes 1. And I do the same with the coefficient vector. And then I solve the coefficient vector. Like, take this element here, and I solve it down. Right? Like, I compute the. No, I don't solve it down. I have to triangularize first. Okay, like triangularization. Okay. Then the second thing. Then I have to take the second row, and I have to basically put here a 0. Am I correct? Do you see anything, guys? Okay. Hello? Sorry. Like, no. Sorry. It was on the triangularization. Okay. Sorry. In order to solve the system, I have to triangularize everything. So, like, the very first thing that I will have to do is to set a 1 here, and then go down and delete all other rows. So, like, once I have a 1 in this column, then I will have to get a 0 here, a 0 here, and a 0 here, just by multiplying this row by the opposite of the potential element that I find in this column. You see anything? Yes. And then sum this to this, so that here I get a 0. And in this way I proceed, and then I eliminate this column. So at the end of this step I will have a 1 here, and then 0 along all this column over here. Okay? Then the second step that I do, like by doing this operation, however, what I was doing is that I was taking this line and summing it all over to the subsequent lines. So I took this line and then I added it here, I added it here, I added it here, and so on and so forth, right? So in this way, when I reach the bottom, I've copied all the contribution of this line and also all the other lines which follow over and over in the bottom part of my matrix. Okay? And then, even if originally I had only elements here, and elements here, by doing this triangulation step, then I end up that I have a dirty, dense system. Okay? Because I rendered all this part of the matrix dense. But in contrast, what happens if I want to triangulate this system and render it easier if I just exchange this column over here and this column over here, and equivalently their row? This will lead me to a system that has this form. Okay? So like what happens when I start my triangularization? Well, I see that this block here, I have this block, I'm super happy that I have this block. It's non-zero, I leave it, I multiply by the inverse just like to make it 1. And then I have to zero all the column, but it's already 0, so I don't need to copy any other value. So doing this operation will not add any sort of filling. When I arrive at the end, potentially I will add something, but I will add nothing. Because this line here is only 0, maybe only this part, so I will add something here. Then I repeat with the second, I repeat with the third, and basically at the end I will have deleted my linear system, I will have rendered it just diagonal, and I will have added basically 0 filling. Potentially I will have some line over here, but this system will end up having a very sparse, so I will not have the last line because I have deleted all elements as I was going down. And actually, like, we went from having a full system to having an empty system just by swapping the first and the last row. Okay? Like, what I was doing is like Gauss-Newton elimination in a pattern of a matrix made with the upper corner and the line, and then the lower corner and the line. And the two matrices are related just like by a permutation, but just by swapping rows and columns. And in one case, I figured out that I end up with a linear system which is very sparse. In the other case, I end up with a linear system which is super dense. Okay? Now, let's go back to me, like other view. Here I am. Hello. Okay. And where is the keyboard? Very good. Now, you understand that it's the key to get a sparse linear system from a sparse factorization from a sparse linear system. This was just to give you an intuition, right? It's not part of the example, not to leave everything completely floating. Is to calculate an ordering of the variables that mostly preserve the sparsity that I find in the original matrix. And to this extent, let me introduce the concept of a permutation matrix, which is a matrix that, if multiplied to the left and to the right by another matrix, just shuffles the rows and the columns. Permutation matrix is characterized by having the elements of a permutation matrix are either 0 or 1, it's square, and it has exactly one non-zero for each row and exactly one non-zero for each column. It's basically a special case of an orthonormal matrix, okay? And also, being a special case of an orthonormal matrix, the inverse of a permutation is its transposed. If you look at what a permutation matrix does, it just shuffles the elements. If you apply the permutation matrix to a vector, you will just like find that the values are not changed, but their order is, okay? Now the game is to, if I give you the structure of a Cholesky factor or of the H matrix, you could calculate with a super complicated NP algorithm an ordering and thus a permutation matrix that preserves the sparsity. The point is that if for calculating such an ordering I spend more time than solving the dense system, this doesn't make sense. However, like there's gazillion of research on that made by cool mathematicians that provided heuristics to solve the problem. The simpler heuristic, if you're interested, is the minimum degree ordering. Anyway, there are libraries that do that. For those that are interested, I will provide links on the page. Now, let's assume that God gives us the perfect permutation matrix. Then we could do the game that we were doing before, just like by using the new permutation. Our goal is to have a L matrix, L, no? The matrix of the Cholesky decomposition that is sparse, because if it is not sparse, we cannot even store in memory the linear system, and thus we cannot solve our problem. So let's start. We have given this permutation from Chol mod, give me the permutation. We want to solve this linear system. To solve this linear system, we ask the oracle for the permutation and we multiply to the right both sides, P and P. No? Then, given that the permutation and its transposed permutation and its transposed are one the inverse of the other, I could safely, means that if I multiply them, I have the identity. And so, given its equation, this is a matrix equation, I can shuffle an identity wherever I want. So happily, I throw in here an identity, which then I blot to P transpose times P. Then I have, this is the magic permutation that if applied to my matrix to the left and to the right, gives me my another matrix that does not change the fill-in, which is the number of non-zero elements, only that I change the ordering of them. Change the ordering of the variables, basically. And here I also do the same with a vector, because if I change the order of the columns, I also have to change the order of the rows here. And I do the same with the B vector. So this operation here doesn't introduce fill-in, so it means that I don't make new elements that were zero, non-zero. I call this matrix H prime, I'm happy, which then by some black means I obtain the Cholesky decomposition that I know it will be sparse, because it's sparse thanks to the permutation P. And then I can proceed by using the previous mechanism, which is L transposed Y, L prime transposed, so I calculate a Y, I resolve the system L prime Y equals minus B, and I resolve the system L prime transposed delta X equals Y. And once I've done that, I obtain a delta X prime. Remember, I obtain a delta X prime, which is the permuted version of X, that then I shuffled, I reorder, if I wanted to preserve this ordering, by applying the inverse permutation, and then I obtain the original vector delta X. If you want to be smarter, given that you know already the structure of the H matrix, you know it because it's encoded in the structure of the measurements, you could directly avoid all this permutation business, and then you could decide that the order of the variables in your vector, the assignment of the variables in your vector, straight away that follows the permutation. In this way you have already the ordering. Fine. Now I arrived at the end. This lesson was heavy and theoretical. I wanted to show you the effects of this sparse factor graph, but I will not manage, and I think you're all boiled. We did not approach, the comments are, we did not approach a complex multi-robot, multi-landmark problem because we did not have time, but we will do it in the next lesson. All right? And these are remember that the sparsity is what really matters when you solve large problems. You have to do the impossible to preserve. Okay? And I would close the lesson here because I baked you, and well, next time there will be also another exercise because I didn't manage today. Have a nice weekend.